Hi and welcome back to my Physics Online Video Lecture Supplement series. In today's video, I wanted to talk about the topic of rotational dynamics, and specifically I wanted to look at rotational motion. This is the first part of this two-part lecture set. In the previous lecture, basically lecture set number 7, I talked about basic rotational kinematics in the context of uniform circular motion. So I considered their motions with constant angular velocity and constant angular acceleration. And I basically introduced all the kinematics terms and put them in context along with their translational analogs, and then I discussed rolling motion. And so what I wanted to do here is move on and talk a little bit about what causes a thing to begin rotating. And that is sort of analogous to the previous lecture in which I talked about forces as the efficient cause, or the thing that causes something to begin moving in a translational manner. And so this one is sort of the analog for rotation. And while we're at it, I'll look at stuff like rotational energy. Before we begin that, I wanted to do a quick review of the rotational kinematics terms. You can see lecture set number 6 for a more thorough review. Basically, you can recall that in rotational kinematics, we specify position by angle, and so usually this right here would represent the position of 0, theta equals 0, and as this wheel rotates counterclockwise, we rotate through the angle theta, and so the new position would be theta, and we've traveled through a total arc length of whatever this radius is, r times theta. And so the angular displacement is then a change in the angular position. So if this is your initial angle and then it rotates over to here for your final position, then whatever this angle here is represents the angular displacement. The angular velocity represents how much this angle is changing per unit time. And the angular acceleration represents how much the angular velocity is changing per unit time. So here are what these terms would be defined in mathematically. These are the translational terms: position, average velocity, average acceleration. And here are the angular equivalents: position, average velocity, average acceleration. And notice that an analog has basically the same equation as an analog. Theta is the angular position, delta theta is the angular displacement, and that's defined as a change from final to initial. X is the actual translational position, delta x is the translational displacement, and the change from final to initial is equivalent to the displacement. If you look at the velocities, omega is basically delta theta over delta t, whereas the translational velocity is delta x over delta t. The angular acceleration is a change in angular velocity per unit time. The translational acceleration is a change in the translational velocity per unit time. Similarly, here are the equations that we saw for the kinematics under constant translational acceleration and under constant rotational acceleration. And it's worth noting here as well that to convert from translation to rotation, you can multiply by the radius of whatever it is that is rotating. So if you want to find the path length around the spinning object, you'd multiply the angle by, or the angular position by the radius, and do that for the angular displacement, and that gets you the path length that you have translated through tangentially. And very similarly, if you have rolling motion, the translation is in fact going to be given by the radius times the rotational angle to get the center of mass translation versus the rotational position to get the translational velocity versus the rotational velocity, etc. So let's do a quick example of that. Suppose that you have a fisherman and he hooks a fish, and the fish accelerates for some time, thereby pulling the line, thereby accelerating the reel. And if we know what the rate of acceleration is, or if we know how many cycles this thing spins through, we can figure out what the rate of acceleration is, and vice versa. So let's go ahead and work this example a little more explicitly. Okay, the first part is that we are given the number of cycles. So if we wanted to get the change in theta, that's going to be 2 pi times the number of cycles through which it's gone through. A cycle is the equivalent of a revolution. So after 60 revolutions, we will have gone through delta theta equals 2 pi times 60 revolutions, or delta theta is equal to 120 pi radians, and that is the correct units for angular displacement. So that's 60 cycles, and this is done in 3 seconds with a constant angular acceleration. So under constant angular acceleration, we can write that delta theta is equal to 1/2 times whatever the angular acceleration is, times the time squared, plus whatever the initial angular speed is, times the time. And presumably the fish is initially at rest when it bites onto the bait on the end of this line. So in this case, we'd have that the delta theta is 1/2 times the angular acceleration times the time squared. So if we wanted to get the angular acceleration, we basically rearrange this equation to get 2 times delta theta over t squared. And so that's going to be 2 times 120 pi radians divided by the time, which was 3 seconds, so 3.00 seconds. That gives us a total angular acceleration of 83.775, so we'll just call that 83.8 radians per second squared. So that is the angular acceleration of this reel. Now, if you want to get the acceleration of the fish, it should be that angular acceleration times r. So that becomes 83.8 radians per second squared times the radius of this wheel, which is 4.5 centimeters, which we would write as 0.045 meters. So what that gets us is a total acceleration of approximately 3.7699 meters per second squared. Since there's 2 significant figures, we could write this as 3.8 meters per second squared. So now we have the angular acceleration of the fish, of the wheel, and we now have the fish's acceleration. This is A, this is alpha. So the next question is, how fast is the reel spinning and how fast is the fish going at this point? So to get the final speed, we take the initial speed plus the angular acceleration times the time. So that's 0 radians per second plus 3.00 seconds times 83.8 radians per second squared. And so that means that the rate at which the reel is spinning should be 251.32. So we'll record that as 251 radians per second. All right, so we've got how fast is the reel spinning after 3 seconds. That is omega final. Now we want to know what is the speed of the fish. So v final should be r times omega final. So that should be 4.5 centimeters or 0.045 meters times this final angular speed, 251 radians per second. So that means that the final speed of the fish should be about 11.3 meters per second squared. So since this is 2 significant figures, we'll say 11 meters per second. So that is the final speed of the fish. We can also figure out how far the fish has traveled in this time, although that should be the number of cycles times 2 pi, meaning this number, times the radius. And so you'd have 120 times whatever is pi times 0.045 meters, and that would be 16.96 meters. So the fish travels about 17 meters during this time. So now we have to ask the question, what causes this angular acceleration? We know that a translational acceleration tends to be caused by a force acting upon the object. So what's going to cause the rotational acceleration? Well, Newton's laws find some sort of analog in torque. At least the first two laws do. The first law we explored actually in the last set of lectures, the set number 9, which was on statics and equilibrium, and that was that when the angular acceleration is 0, then the net torque acting on an object must also be 0, where torque is given by the force times the radius times the sine of the angle between the force and the radius. So that was Newton's first law analog. Newton's second law analog actually establishes the condition for rotational dynamics. The simplified form of Newton's second law, as normally stated, is that the sum of forces acting upon an object should be the total mass of the object times the object's acceleration. If we're talking about rotational motion, however, this becomes the sum of torques is equal to the total moment of inertia of the object, sometimes called rotational inertia, it's more often called moment of inertia, times the angular acceleration. So recall that the mass of an object is sometimes called a measurement of the object's inertia. So this is a measurement of the object's rotational inertia. The moment of inertia itself is a scalar quantity because it measures the inertia in rotational terms, as opposed to the mass, which also is a scalar quantity, but which instead is measuring the inertia in translational terms. You could think of both as a resistance to change in motion. The mass is a resistance to an acceleration, a translational acceleration. The inertia is resistance to rotational acceleration. And in fact, the inertia, the moment of inertia actually depends upon the mass of the object in question, but it also depends upon how that mass is distributed. For a single point object, or for a single object which is very small compared to the radius of its orbit, you can calculate this moment of inertia very quickly. It's the mass of the object times the rotational radius squared, or times the radius squared about which it's rotating. And the axis of rotation has to be determined first in this case. Now, when we talked about equilibrium, the axis of rotation could be chosen at will because the object wasn't actually rotating. That was the whole point of equilibrium. If the axis of rotation provides 0 torque for one axis, then any choice of axis will provide a net torque of 0. In the case of rotational dynamics, where the net torque is not 0, it's helpful to first figure out what axis the object is actually rotating about. And if there are multiple point objects about a common axis, then the rotational inertia of the set of objects can be added together to get the total moment of inertia for the system. So that means if you have, for example, 2 point objects that are rotating about a common axis, then you take the rotational inertia of the first and you add it to the rotational inertia of the second, and that gives you the rotational inertia of the system. So let's do a quick example using what would count as point objects with a common axis of rotation. So we're going to pick the axis of rotation to be the z-axis, and then we're going to do it again with the axis of rotation being right here, located in the center of this particular point mass. So each of these basically is representing a point mass for this example. So the system's rotational inertia can be found as follows. The total moment of inertia for the system is given by the moments of inertia for object 1, object 2, and object 3. We'll label these 1, 2, and 3. So moment of inertia for the first case, First case is the axis of rotation is located right here. All right, so if that's the case, then we need to figure out how far away each one of these is from that axis of rotation and what the mass is. So for object 1, it's located 2 meters, 0 meters. That's 2 meters away from this axis of rotation. It's 2 kilograms. So I number 1 is m1r1 squared. That's going to be 2.00 kilograms times 2.00 meters squared. So I1 would be 8.00 kilogram meters squared. I2 we calculate the same way. It's going to be m2r2 squared. So this one is 0, 1, so it's 1 meter away. It's 3 kilograms, so 3.00 kilograms times 1.00 meters squared. So I2 is given by 3.00 kilogram meters squared. Finally, we have the moment of inertia for object number 3, which is located right here, 4 meters, 0 meters. So that's 4 meters away, so m3r3 squared becomes 4.00 kilograms times 4.00 meters quantity squared. So 16 times 4 is 64. That means that I3 is 64.0 kilogram meters squared. So the total moment of inertia, therefore, is given by 8 kilogram meters per second squared plus 3 kilogram meters per second squared, meters squared, plus 64 kilogram meters squared. So 11 plus 64 gives us 75. So the sum of these moments, or the total moment of inertia, is 75.0 kilogram meters squared. So that's what happens if we pick this to be our axis of rotation. What happens, though, if instead we make our axis of rotation be located right here? So if our axis of rotation is located over here, then we have to figure out how far away each one is. So we still can write that the total moment of inertia is I1 plus I2 plus I3. And now what we have to do is figure out how far away each of these guys is. Well, for I number 1, we would get a moment of inertia of 0, because this object is located in the same spot as our axis of rotation. So 0 kilogram meters squared. I2 is the one that we're going to have to actually do something with. It's located here. So how far away is this from our axis of rotation? Well, it is up 1 and over 2. So 2, 1. So this distance, R2 squared, should be 2 squared plus 1 squared. So that's 4 plus 1, so that should be 5 meters squared. So I number 2, remember, is mass 2 R2 squared. So that would be 3.00 kilograms times 5.00 meters squared. So I'm just not even going to bother taking the square root of this since I don't really need it. That means that I2 is 15.0 kilogram meters squared. Now for I3, we have 2 to get to here, and then another 4, so that's 6. So when we do m3r3 squared, what we really have is 4.00 kilograms times this distance, which is 6.00 meters quantity squared. So 36 times 4, which gives 144 kilogram meters squared. So I3 is 144 kilogram meters squared. So the total moment of inertia is going to be 15 plus 0 plus 144. And by my math, that makes 159 kilogram meters squared. So actually, little over twice as much as if you took this to be your axis of rotation. All right, so what about finding the moment of inertia for a solid object? If you have a solid object, or even a large collection with many, many individual point masses, you basically treat it as follows. You take each individual point mass and you find what the distance from the axis of rotation is. You then multiply the mass times the radius from the axis of rotation squared. Then you add up all of these individual masses times all of these individual distances, and when you've added everything up, you've now got the moment of inertia for a large solid object, or for many, many individual smaller masses. If you want to treat this more rigorously, you might want to use calculus, and that basically changes this sum into an integral. Let's look at a quick example of finding the rotational inertia for a cube. And the way we're going to do this is we're going to start off with an axis of rotation which passes through this cube and is parallel to these four lateral sides but perpendicular to the top and bottom. The question is, given that the moment of inertia for this particular axis of rotation is 1/6 times the mass of the cube times the length of each side of the cube squared, what would happen if we were to move this dashed line over to one of the corners of the cube? So one way of looking at this is that instead of having a single cube here, we could take this cube and divide it up into sort of portions. And the portions basically are chopped like this. So each single cube like this has become instead 8 individual smaller cubes. So here's one individual smaller cube. And you should notice that this axis of rotation now passes through one of the corners of the cube. That's what we're wanting to do here anyway, is have the axis of rotation pass through the corner of the cube. It's passing through one corner of the cube, and each of these 8 cubes is equal as far as moment of inertia is concerned compared to this axis. So that means that a small cube, we'll call it small cube, would have I equals 1/8 of big cube. And the big cube here is basically 1/6 mb squared. So each of these little cubes would have 1/6 times m/8 times b squared as their moment of inertia. Well, that means that if you were to design a axis of rotation that passes through the corner of one of these cubes, say this corner right here, that you could always draw another 8 cubes that are of the same size that this, like so, such that this axis of rotation now passes through the center of this set of cubes. So this is a set of 4 cubes. If we wanted a set of 8, then we basically need to extend off this way and draw on a cube here, draw on a cube here, etc. So we've now made a cube that is 8 times the size of this big cube. And so the moment of inertia for the new cube, because each of these sides basically ends up having a 2 times b as the length of a side, and the mass is now 8 times as big because there's 8 times as many, then I big would be 1/6 times 2b squared times 8 times the mass. And I original, this is I of the smaller cube, I small equals 1/8 of I big. So that means that if you were to move the axis of rotation through one corner of the small cube, then you have 1/8 of all this, so we basically need to divide this by 8. That cancels out, and so you end up with I small equals 1/6 times 4b squared times 8m divided by 8. And so I small, which is what we're really looking for here, is 4/6 is equal to 2/3 of m times b squared. So this is basically 4 times as much as the moment of inertia of this smaller cube here. So I went ahead and put the moments of inertia for quite a few composite objects, given this green line in each case represents the axes of rotation. And so, for example, if you have a hoop, which is the same thing as a very thin ring, then you get I equals mr squared. The mass is m. If you have an annular cylinder, that's basically a ring that has an inner and outer edge and some actual thickness, then it becomes 1/2 times the mass times the sum of the squares of these two radii, and so on. So here are some balls. Here's another hoop with some diameter that's spinning about the axis that is passing through edges instead of through the center. In other words, this ring you could think of as spinning out and into the page. Here's a slab with sides a and b, so m equals a squared plus b squared over 12. And of course you already saw what a cube is with the axis of rotation through both the center and through one of the corners. Alright, so let's look at another short example. Suppose you've got a thin, solid cylindrical rod, and instead of placing the axes at any of the points that are being shown here, you place it 1/4 of the distance from one end of the rod. So what's the moment of inertia going to be for this rod? All right, well, placing it 1/4 of the distance from the end, we can use something that says, let's say that L1 is 3/4 of L, and L2 is 1/4 of L. All right, and M1 is going to be 3/4 of M, and M2 is going to be 1/4 of M. In other words, we're going to split the rod into 2 rods. One is like this, the other continues the other 1/4 of the way, and our axis of rotation is here. This total length right here is L. This length right here is only 1/4 of L. So the total mass is m. This is 1/4 of m. This is 3/4 of m. Well, you can see that a thin rod, which is rotated about a axis which is perpendicular to the rod and is through one end, has a moment of inertia I equals ml squared over 3. So we would use something like I1 is equal to m1 L1 squared over 3, and I2 is m2 L2 squared over 3. And I total, I of the rod itself, has to be I1 plus I2. So we use I1 is equal to M1, which is 3/4 M, so that's 3/4, times L1, that's 3/4 of L, so 3/4 L squared divided by 3. So we can cancel out a 3 if we so desire, and in any case this is going to be 9/16 times 4, which is 9/64 of L squared. I2 is going to have 1/4 M times 1/4 L squared divided by 3. So that's going to give us 1/4 times 1/4 times a 4th is a 64th, divided by 3 is 1 over 192. So this would be ml squared over 192. This one, for what it's worth, would be 27 ml squared over 192. So the total moment of inertia should be 28 ml squared over 192, which is equivalent to 7/48 of ml squared. So you can see that this moment of inertia is a bit smaller when we put the axis of rotation part of the way through the rod, and that kind of follows what the pattern is. If it was midway through, you'd have ml squared over 12. This is very nearly equal to 2/12 or to 1/6, but not quite. Another example gives us a thin hoop with some width and some radius and some mass, and the question is, what is the moment of inertia of this hoop? Now, you may be tempted to look at this and say, oh, okay, we're talking about this hoop right here, and the moment of inertia is I equals mr squared. So we would say something like I equals 4.00 kilograms times the radius, which was 0.25 meters squared. And so you'd end up with a moment of inertia of 0.25 kilogram meters squared. The thing is that this is not the hoop that we're actually looking for. And the hint is that we're talking about an axis through the central diameter. So that means that we actually want to do this hoop right here. So wrong, right. And so this is the equation that we're going to be using. What this diagram is showing, by the way, is if we were to look at the hoop end on, then the axis of rotation looks like this. And if we were to look at it from the side, then the hoop basically is going to look something like this, and the axis of rotation is cutting through the center. And so this one and this one are both rotating in and out of the page. So it basically would be rotating from this condition to this condition, back to this condition, and so on. So the moment of inertia is 1/2 of mr squared plus 1/12 mw squared, where w is the width, r is the radius. All right, so this moment of inertia, therefore, is 1/2 times the mass, which is 4.00 kilograms, times the radius squared. The radius squared would be 0.25 meters squared. So in other words, this term right here actually should be equal to this part. And then to that, we're adding another 1/2 times the mass. So another 1/2 times 4 kilograms times the width squared. So the width is 5 centimeters, so that's 0.05 meters squared. And I misspoke a second ago. I said that this part would be equal to this part. It's actually half of this part. So our total moment of inertia for this entire hoop would be about 0.13 kilogram meters squared. So notice that this right here is actually a little over, but just barely over, half of the moment of inertia we would have calculated had we attempted to calculate for a hoop that is spinning in this direction. So how is it that the torque affects the angular acceleration? Well, we saw this equation on a previous slide, but just to remind us why we're calculating all of these moments of inertia, the sum of torques acting upon an object should be its moment of inertia times the angular acceleration. So generally speaking, the moment of inertia is staying constant for an object. This is not always true. For example, you might have a child who's on the edge of a merry-go-round and who's being spun up by another child. And so the second child is applying a torque to the system, but that first child maybe starts to walk towards the center of the merry-go-round. We'll get into this more complex version in the second part of this lecture when we talk about angular momentum. For now, we're going to basically assume rigid objects so that the total moment of inertia is actually a constant. Let's look at an example of this in action. Suppose you have a merry-go-round with a rider, and then a second child is trying to spin up the merry-go-round. What's the angular acceleration going to be, assuming that the bars of the merry-go-round themselves have negligible mass? Okay, so the scenario is that you've got a child who is basically running around this merry-go-round, pushing on the merry-go-round so that the merry-go-round will spin. So there's going to be some angular acceleration of the merry-go-round as a result of that. These bars have negligible mass, so the merry-go-round itself has a given radius, a given mass, and can basically be treated as the same thing as a solid disk. So the solid disk from the previous slide has a moment of inertia of 1/2 times the mass times the radius squared. And in fact, you can get that from the same way as you get for a hollow cylinder or an angular ring, by taking the limit where the inner radius is 0. So that gives you the same result as the solid cylinder either way. So basically we write I is equal to 1/2 mr squared, and the sum of torques is equal to the moment of inertia times the angular acceleration. So all of this basically tells us that the angular acceleration should be equal to the torque from the child divided by the moment of inertia. We're assuming that this is basically frictionless, so no friction for this merry-go-round. All right, well, the torque is going to be given by the force that the child is applying. So tau is equal to R cross F. And so that means there's basically going to be the radius times the force. Sine of the angle should give us 1. This is then being divided by 1/2 of mr squared. This radius and this radius are equal, so we can cancel out the squared part of this r with this r. You end up getting that the angular acceleration should be 75.0 newtons divided by the half. So a half in the denominator is the same as 2 in the numerator. And then the mass is 60 kilograms. And the radius is 2.50 meters. So what this gives us is a total angular acceleration of 1.00 radians per second squared. The other part of this example is, suppose that the child is now riding on the edge of this merry-go-round and somebody else is trying to supply the force and hence the torque in order to spin this up. How much force would they need to supply in order to get that same 1 radian per second squared acceleration? All right, so again, we can write that the torque should be the total moment of inertia times the angular acceleration, and that the torque is the radius times the force being applied. So this collectively means that the force should be the total angular acceleration times the total moment of inertia divided by the radius. Now, what's this total moment of inertia going to be? Well, you have one moment of inertia for the merry-go-round, I sub m, which is 1/2 mr squared. You have another one because there's now a child who is happily riding on the merry-go-round out here some distance r away from the axis of rotation. So this distance is r. Here's the child. The child has some mass. The thing we need to know is how much mass does the child have. And so a typical child might have a mass of, let's say, 30 kilograms. So we'll make m child be 30 kilograms. If that's the case, then we're going to have a total moment of inertia that's given by I total equals I child plus I merry-go-round. So that is going to be mass of child times radius squared plus 1/2 times the mass of the merry-go-round times the radius squared. All right, so this then becomes basically, if you wanted to stick all this into the forces equation, you'd have force equals mass of child plus 1/2 of the mass of the merry-go-round times this radius squared times alpha divided by the radius. So again, we can cancel out one radius, and what we're left with is that the force should be 30 kilograms plus 60 kilograms times a half times 1.00 radian per second squared divided by nothing down here, and then times another radius, which is 2.50 meters. All right, so the total force should be given by 30 plus 60 over 2 is another 30, so that's 60 times 1 times 2.5. That gives us 150 newtons. So we need twice as much force if this is the case. If the child weighs half what the merry-go-round weighs but rides out on the outer edge, then we will need twice the force that we needed before. So that is torque, and that is how torque and rotational acceleration tie together. So now I wanted to move on to the next topic in rotational motion, which is kinetic energy. So in a previous lecture, I discussed translational kinetic energy. That was basically lecture set 7. And for a given object, the translational kinetic energy is half of the object's mass times its speed squared. If you have an object which is just simply rotating without translating, there's still some motion to that object, and that means it still must have some kinetic energy. So the kinetic energy is associated with the rotation of the object, and it will still have units of joules because that's the unit for any kind of energy. And basically the way that you get the rotational kinetic energy, one way you can get it is as follows. You have an extended object which can be broken up into point particles. Each point has a rotation that follows the rotation of the whole. So if the whole thing is rotating with a speed of omega, then this particle is rotating with an angular speed of omega. The mass of the particle is mi. The instantaneous speed of the particle is whatever the instantaneous rotational speed is times the radius from the axis of rotation. So if we want to get the total kinetic energy for this whole big object, we take all of these individual points or elements that make up the object. We figure out what their kinetic energy is, 1/2 mv squared. We add all that up. We recall that v is equal to r times omega. So basically we end up with 1/2 mr omega quantity squared, and m times r squared for a given point is the moment of inertia. So we can rearrange this equation to get that the kinetic energy is 1/2 of the total rotational inertia times the angular speed squared. Therefore, if you want to restate the conservation of energy, what you do is that you take the total energy before and it's equal to the total energy after, once for an isolated system, assuming that you have some propulsive work and some dissipative work. Set any terms equal to 0 as needed. So the work energy theorem can be generalized to say that the total non-conservative work is going to be equal to the change in translational kinetic energy plus the change in rotational kinetic energy plus any change in potential energy for the system. All right, so this brings me to the question of what about work done against a rotating object? Well, as you know, if you change the rotational speed of the object, then you've got to change the rotational kinetic energy and hence the total kinetic energy. This is because the rotational kinetic energy is 1/2 times the moment of inertia times the rotational speed squared. So if you change the rotational speed, you can see that you're going to be changing the rotational kinetic energy. Now, the work done on or against the object must be equal to that change in rotational kinetic energy. For example, if we assume that the object is only rotating, there's no translational motion, no changes in potential energy, and it's an isolated system, then the work kinetic energy theorem says that this change in rotational kinetic energy must be equal to the work. the thing isn't additionally translating, then the work can be given by the change in both types of energy. In any case, the work done in general on any object is always going to be the net force times the displacement. This is the dot product between net force and displacement. So it's force times distance times cosine of the angle between the two. So if you have a rigid object and some force is applied a distance r away from the axis of rotation, then this displacement delta s must be given by the angle through which the thing has rotated times the distance between the point at which the force is applied and the axis of rotation. So let's consider this rigid object, and let's consider this force. It's going to have to be in the same direction as delta S. So for example, if you have the child pushing the merry-go-round, they're running around this merry-go-round, and basically they follow this curve delta S, and assuming that they just continually push straight ahead as they follow this curve, then the direction of this force is going to also be changing as they pass around the curve. Hence, the effective net force is going to be in the same direction as this displacement. So the torque, therefore, which is given by r cross F, is just going to be r times the perpendicular force. So this perpendicular force is always parallel to delta S. It's always perpendicular to r. Therefore, the net torque is always r times F. And if you want to find the work, it's got to be whatever this perpendicular force is times r delta theta. R times F perpendicular gives you the torque. And so the work must be the torque times the angle through which you pass while applying that torque. And this basically is going to contribute to the change in the rotational kinetic energy. Let's look at the other side of the work kinetic energy theorem. We'll start with Newton's second law as applied to torque, which says that the net torque is equal to the moment of inertia times the angular acceleration. Well, if you have a constant angular acceleration, you can go back to the kinematics equations, and you know that the angular speed squared is equal to the initial angular speed squared times twice the angular acceleration times the angular displacement. This equation is valid as long as you have a constant angular acceleration, which is the same thing as saying a constant torque and a constant moment of inertia. This equation, you can go back and review your kinematics lectures, which were the lecture set 6 and also the earlier lecture set number 2 for translational terms, because this equation is also there in the translational kinematics. I also believe that I have it earlier in this lecture set. In any case, we can solve for this term here and substitute into the equation for work to get that work is half of the moment of inertia times the final speed squared minus half of the moment of inertia times the initial speed squared, which is the same thing as the change in the rotational kinetic energy. All right, so I'll do that explicitly now. Work, as we saw in the previous slide, was the torque times the angular displacement. And the torque is I times alpha, the moment of inertia times the angular acceleration. Finally, the kinematics equation was omega squared is omega initial squared plus 2 times alpha times delta theta. So alpha times delta theta is going to have to be the difference in the squares of these speeds, these angular speeds, divided by 2. So torque is I times alpha, work is torque times delta theta. These two combine to say that work is equal to I times alpha delta theta. Well, that is going to be equal to I times, by substituting this in, omega final squared minus omega initial squared divided by 2. All right, well, that's the same thing as 1/2 of I times omega final squared minus 1/2 of I times omega initial squared. That's just distributing the I in the half. Finally, this right here is the same thing as the initial kinetic energy, as the final kinetic energy. This right here is the same thing as the initial kinetic energy, rotationally, of course. So this difference, therefore, is collectively going to be equal to delta E K R, or KER. It's the change in kinetic energy. So that is the work energy theorem as applied to rotational mechanics. All right, let's look at a few short examples here. What's the rotational kinetic energy of a bicycle wheel whose rotational speed is 25 radians per second and whose moment of inertia is 2 kilogram meters squared? Well, the rotational kinetic energy, EKR, is given by 1/2 times the moment of inertia times the angular speed squared, or rotational speed squared. So that is going to be 1/2 times 2.0 kilogram meters squared, because this term right here is the moment of inertia. This term right here is the angular frequency or angular speed, or rotational speed, so that's 25 radians per second. We're going to square that. If you do all that, then you get 1/2 times 2, which is 1, times 25 squared, which is 625. So this has a kinetic energy of 625 joules. Okay, second question, how much work do we need to bring this above bicycle wheel down to a rotational speed of only 15 radians per second? All right, well, the work should be the change in kinetic energy, EK. And we're basically assuming that the bicycle wheel is free spinning, so it's not like rolling while spinning, it's just simply spinning. So this would be 1/2 of the of the final rotational energy minus 1/2 of the initial rotational kinetic energy. All right, well, again, I was equal to 2.0 kilogram meters squared. And so this work we could write as work is 1/2 times I times difference in rotational speeds. So this one right here was 25.0 radians per second. This one right here is 15 radians per second. So this one right here squared becomes 625 radians squared per second squared. This one right here becomes 225 radians squared per second squared. This difference between the two, therefore, is 400 radians squared per second squared. And actually, I've accidentally flipped which one's which. So really it should be negative 400. These all belong with the initial. These all belong with the final. The total work done, therefore, is 1/2 times 2 kilogram meters squared times negative 400 radians squared per second squared. So the total work done should be 400 joules, or minus 400 joules, if you will. And that's to slow this wheel down to only 15 radians per second. All right, now let's assume that the bike is actually traveling through 16 revolutions while slowing from this rate. So the question is, what torque must have been applied in order to get from 25 radians per second to 16 radians per second over a course of 16 revolutions? Well, the moment of inertia should be multiplied by the angular acceleration to get the torque. So tau equals I times alpha. So what we need is to figure out what the angular acceleration alpha is, and then we can get the torque. Well, the angular acceleration alpha times 2 times the angle for which this thing passes should be equal to this difference in angular speed squareds. So alpha should be equal to omega final squared minus omega initial squared divided by 2 times the angle through which we pass. So this becomes a total of 15 radians per second quantity squared minus 25 radians per second quantity squared divided by 2 times 16 revolutions times 2 pi radians per revolution. All right, so there's that. And so the angular acceleration, recall, of course, that this number is what we calculated in the previous problem as minus 400 radians squared per second squared. So the actual angular acceleration should be just shy of 2 radians per second squared. It's actually 1.99 radians per second squared. So this means that the total torque should be that times another 2. So that means we should now be just shy of 4 radians, just shy of 4 Newton meters. So that would be 3.9788. And in fact, if we were to round off to 2 significant figures as warranted by these numbers, this would actually give us a total torque of approximately 4.0 Newton meters. So that is how much torque is needed to do this much work. Now, of course, we could have done it the other way around by basically finding that work was equal to torque times delta theta. So we could have also found the torque by taking the work and dividing by this angle that we passed through, where the work is what we found in the previous problem. Either way should get us the same answer. And finally, we're basically finding the magnitude here, which is why I dropped the minus sign. Okay, so that is our brief lecture on rotational motion. We covered in this lecture concepts such as torque and how it applies to angular acceleration and moment of inertia. And then I also looked at energy from a rotational perspective and the work energy theorem from the same perspective. And so that's quite a few topics, but recall that a lot of this was also review from previous lectures. So although it seems like there's a lot of material here, it's really, in a sense, a synthesis of a number of the previous lectures. And so this now might be a good time for you to go back and review a few of the old lectures and see how they tie into this one. In the meantime, I hope that you enjoyed watching this video, and I hope that you find this video helpful. And thank you for watching.